Hello everyone, my name is Eduardo and this is my video lab report for Lab 4 for Physics 2211. In this lab we're going to analyze two-dimensional oscillations and compare real-life observations with a computer model simulation and see how we can take conclusions from the graphs of the energy changes. We're going to, as always, use Newton's second law, but we're also going to use some new concepts such as the spring force, which we can see the formula for here, which involves the spring constant and the extension of the spring compared to its relaxed length. And we're also going to use this formula that um, relates the spring's period of oscillation with the mass of the object and the spring constant, so we can calculate the spring constant. And we're gonna get that from the tracker analysis later on. This is the video I used as the experiment for this lab. As we can see, there's clearly a two-dimensional oscillation caused by the spring, and in the computer simulation we're gonna use, I assumed the system was only composed by the spring, the object, the mass, and the earth, but in reality there is a bit of drag force caused by the motion, which kind of ruins the analysis, but not too much. You can see that here on tracker. Um, if we look at these two graphs for the x and y positions of the mass, we can see that up until about the third oscillation, their periods are about the same, but after that they diverge a bit, and that's most likely because of this difference in the drag force in both directions. I also use this tracker analysis in order to plug it into the simulation to compare our real life observations with the computational model result. Here's my glow script code for this lab. Here's the mass I used, which I got from the lab instructions, and here's the initial position velocity, which I got from the video I used to analyze in tracker, as well as the delta t I used in the simulation. In this line, you can see how I calculated the springs constant with the method I mentioned previously. And here I got the relaxed length of the spring by setting the spring force at the start of the video equal to the gravitational force, because since the mass is at rest, both forces have to be equal. And here I just set up the necessary information to use the spring extension vector. Here is the most important part where I calculate the kinetic energy, K equals mv squared over 2, the potential energy due to gravity, which is just mgh, and I'm using the origin as the referential for the gravitational potential energy. And the spring's potential energy is just ks squared over 2, where s is the magnitude of the spring extension in relation to its relaxed length. And the total energy is just the sum of these three. In the simulation, we just do the regular algorithm. We calculate the net force for due to the spring and gravity, update the velocity, then with this new velocity update the position, with this new position update the spring vector, and so on repeatedly. And then we update the energies respective to each force and calculate the differences so we can plot the graph. And this is how it ended up looking. As you can see here in the x and y comparison, they're very similar, comparing the experiment and the model, although the y position is a bit different, but that's possibly because of my error when measuring stuff on tracker. And um, here we can see there's a bit of changing total energy, and that's probably because of the iterational method for the simulation, which causes a bit of error when we calculate the velocity for the kinetic energy. But besides that, we can clearly see that the energies kind of switch between each other, and in general, it's very much conserved throughout the whole experiment. In conclusion, we can see that spring mass systems don't need to be bounded to just one dimension, but we can still model them in those more complex situations with more dimensions based on the energy principle. And although we did get um, slightly varying values for the period, we can still calculate the period um, of the spring's oscillation using both x and y directions if we account for those minor errors.